All right, hello everybody. Welcome to the first video for section 3.8. So we're skipping over 3.7 and or just 3.7 for right now. We will come back to it. But we're moving on to 3.8. And I like this meme that we have here, even though I know it would not relate to any of you, because I know you all are just loving this calculus thing and are not feeling at all like James Van Der Beek in this picture here. Okay, so section 3.8 is about something called implicit differentiation. We'll get to what that means. So first thing I want us to think about is how could we find the derivative of this function here? So x equals y to the sixth. Now, first of all, when you look at this, I imagine that there is something that stands out to you, right? And hopefully that thing is that this is in the form of x equals something instead of y equals something, right? So with that in mind, one way we might think about taking the derivative here is instead of having this function written as x equals y to the sixth, well, first of all, hopefully you would agree with me that the way it's written, it looks like y would be the input variable and x is the output variable here. And so we could write this as a function that instead of its f of x could be f of y equals y to the sixth. And then to take the derivative, right, well, it looks like we can just use our power rule here. And so we would end up with f prime of y equals 6y to the fifth. And go from there, right? So that's one way we can think about this, or one way to approach this. However, we know that generally, and against, I will say this begrudgingly because those of you that have been taking classes with me for a while know that I like to hammer home the fact that the only variables in the world are not x's and y's, and we can't always assume that those are the only inputs and outputs. But what if we want to find dy dx here? And I know we've used this notation d dx before. Okay, and that usually means the derivative with respect to x. That dx part on the bottom means with respect to x. But here they want us to find dy dx, which what this is really saying when it says that is the derivative of y with respect to x. So we want to find the derivative here, kind of with the assumption that y is a function of x rather than x being a function of y. But that might seem a little hard to do because of the way this function is set up. So what can we do? Well, one thing would be to maybe try to isolate the y, so maybe take the sixth root on both sides, but that gets a little messy. So this is where this idea of implicit differentiation comes in. Okay, now for implicit differentiation, in the back of our minds, we want to think of y here as a function of x. Okay, now we don't know what that function looks like because we don't know what the formula for it is. But we want to think of y as a function of x. And so what this function is really looking like here then is x equals, instead of y, we have some function of x. And again, the formula for that could be many things. It could be a linear function like 3x minus 1, or something more complicated like e to the x, or log of 3x minus 2, something along those lines. We don't know what it is. But it could be something like this, x equals f of x to the sixth power. And if we want to take the derivative here, right, well, on the right-hand side, notice we have the f of x raised to the sixth. Looks like we have a chain rule example here because we have a function within a function, right? We have the f of x within something raised to the sixth power. So we could use our chain rule here and do the derivative of the outside. So that's 6. Evaluated the inside, so f of x raised to the fifth. So we use the power rule there. Times the derivative of the inside, which would be f prime of x. Okay, and again, we can't say much more than that because we don't actually know the formula for f of x. And I want you to notice that when we do that, this what we have right here, this f prime of x, since it's y as a function of x here, that is actually the same as dy dx. Okay, so that would be the derivative of y with respect to x, because f prime of x is a derivative and y equals f of x. Okay, so let me back up here. Well, actually, one more thing before I do this next thing. So that's taking the derivative of the right-hand side. But notice on the left, and I don't know where that arrow just came from, sorry. On the left here, we still have an x, right? And we're doing dy dx, which means we're taking the derivative with respect to x. So over there on that side, we also need to take the derivative. So the derivative of x using our power rule would just give us 1. Okay? So here you can see we kind of take the derivative on both sides of the equal sign. Interesting, right? I know. Okay, but let's look how this works using the variables, because we don't have any f of x's here. We just have x's and y's. So here's how this works. Because we know y, again, is an implicit function of x, so we're keeping this kind of in our back minds, this y equals f of x thing. We're going to take the derivative on both sides, and here's how it's going to work. So on the left-hand side, we'll take the derivative of just the x. Now we're taking with respect to x, so we can just do it like we just did before. So because this is a function with respect to x on the left-hand side, we'll use our power rule and just end up with 1. Now on the right-hand side, we're also going to take the derivative, okay? And we're still doing it with respect to x, but we'll start off by just taking the derivative of this y to the 6th like we would if this was a function of y. So we just take derivative of y to the 6th using our power rule, which would be 6y to the 5th. Okay, so nothing crazy there. But then we have to multiply by, again, because y is a function of x, okay, this is really like 6 times f of x raised to the 5th power. If you remember from what I was just explaining, we have to use the chain rule to multiply by the derivative of the inside function, which in this case is y, which we're going to call dy dx, right, instead of using the f prime of x. And then at this point, we're trying to find dy dx. So what we need to do over here is just isolate this dy dx. So we can do that by dividing by the 6y to the 5th on both sides. Okay, and what that gives us, and actually I'm going to write it over here because I have more room, is dy dx, so the derivative of y with respect to x, is equal to 1 over 6y to the 5th. And there's our derivative. Whoa! Kind of crazy, right? Because we end up with a y in our derivative. But that's totally okay. And in fact, at this point in your mathematical careers, depending on where you've been taking your math classes, you probably haven't seen a whole lot of functions that are like x equals y to the 6th, or y, or x is a function of y. But these are often examples of what we call conic sections. And these are functions that, based on our knowledge from 141, okay, they usually would not pass the vertical line test. So the graph of x equals y to the 6th might look something like this, what I've drawn in the upper left-hand corner there. And so even though they're not considered functions through that lens, we can still talk about rates of change with them and tangent lines. And so that's part of why we're taking the derivatives here, also part of why we end up with a y in the derivative. Okay, cool stuff, right? Okay, let's do another example. So here now, we have this function, and actually, yeah, we'll call it a function. They want us to find the derivative of y with respect to x. And the function here is x squared plus y squared equals 16. Okay, so hopefully some of you recognize this function, or this form of a function, as the equation of a circle. Okay, and of course that didn't draw. Here we go. So you recall from Math 142, we see something like this and not like that, like this. Okay, that's representing the equation of a circle with radius 4. And yes, I know my circle is terrible there, but hopefully it gives you a visual. Okay, so I want to take the derivative here. Now, just like on the last one, we need to take the derivative on both sides of the equation. And we also know that when we have stuff being added over here, we take the derivatives of each term individually. And I also want to point out we're taking the derivative with respect to x here. Okay, so for the first term, the x squared, well, that's a function that contains the variable x. So that one we can just take the derivative of as we know and get 2x. For the second term, that plus y squared, well, now that's a function that has y as its variable. So this is kind of like on the last one we had that y to the 6th. So what we'll do is we'll first of all take the derivative with respect to y. So this would be just 2y using the power rule. But then because of the chain rule, as we saw, because this is a function of y, we need to multiply by dy dx. Okay? Because we're assuming y is an implicit function of x. Equals, then we take the derivative of the 16, which is 16 is a constant. So now we know the derivative there is 0. So our derivative is looking like 2x plus 2y times dy dx equals 0. And again, we're trying to find dy dx, so we need to isolate that term there. So we'll subtract 2x on both sides. So we'll end up with 2y dy dx equals negative 2x. The 2y is being multiplied by the dy dx, so we can divide by the 2y on both sides. And on that right-hand side, those 2's will cancel. And so we end up with then that dy dx, in this case, equals negative of x over y, which is kind of cool because now we could find slopes of tangent lines and even equations of tangent lines to the graph of a circle, which is relevant for us because, as we know, there's some astronomical objects that move in mostly circular shapes, or at least ellipse shapes. So we see we could find some tangent lines there, some derivatives there, which might be helpful for finding, say, velocities of objects moving in space. All right. Okay, now I'm really going to mix it up on us. So now we're going to find dv dt for this function. So we want to keep in mind here that we're doing this with respect to t. Okay, and we're doing dv dt. So in this case, we're kind of thinking as t is our input variable, v is our output variable, which we've seen examples like that before. And yeah, let's jump into this. Let's see what happens. Okay, so we'll start with the first term there, the 4t to the third. So we're taking the derivative with respect to t. So there, nothing too complicated to do. We can just use our power rule. So that'd be 12t squared. Then for the derivative of v to the fourth, well, that's kind of like our output variable, or a thing that we think of as being an implicit function of t, right? So what we'll do is take the derivative there. So use the power rule. So we get 4v to the third. But then because it's an implicit function, we use our chain rule and multiply by dv dt. Plus, all right, now here's where it gets really fun. So we have this t times v here. And you're probably thinking, Cody, what kind of madness is this? We now have two variables, different variables being multiplied together. You didn't show us how to do this. this problem's probably impossible. But don't worry, my young potty ones, we can figure this out. So first of all, notice what we have here, even though we have two different variables, is we really have two functions being multiplied together, right? We have t and v. So to find the derivative here, we'll use our product rule. So we'll do the first function, which is just t, times the derivative of the second function. Well, the second function is just v. So taking the derivative there using the power rule, we'll end up with just 1. But then because it's v, a variable v and not t, we have to use the chain rule to multiply by dv dt. And so that times 1 just gives us dv dt. Plus, then we do the second function, which is v, times the derivative of the first, which is just a t. So that would be, derivative of that would be 1. So we just have v times 1, or v. And then take the derivative of 23, that's a constant, which is 0. And recall again, you always need to take the derivative of both sides of the equation with these types of functions. Okay, so look at this fun thing we have here. So right now we have 12t squared plus 4v cubed dv dt plus t times dv dt plus v equals 0. And now we need to still find dv dt, which means we need to isolate the dv's dt's, right? Notice we have two terms with dv dt in them. So what we'll start by doing is moving the ones that don't have dv dt to the other side. So we'll subtract 12t squared, subtract v, and do the same thing on the other side. And so when we do that, it looks like we end up with 4, not that color though. We have 4v cubed times dv dt plus t times dv dt equals negative 12t squared minus v. Okay, and I'm going to erase some stuff up here. So notice now on the left-hand side of our equation, we have two things being added together, but both of those things involve a dv dt. So what do you think that means? Right, we can factor that out because it's in both of them. So if I move back up now, I can write this as dv dt times 4, I think did I write that wrong? Why do I have, oh, okay, sorry. Yep, we're good. So 4v cubed plus t equals negative 12t squared minus v. And then we need to finish off. Now we have dv dt times something, and I know it's a big something, but we can still just think it's something times something. So to isolate the dv dt, we just divide by 4v cubed plus t, divide by 4v cubed plus t. And so when we do that, these will cancel. And here we have dv dt equals negative 12t squared minus v over 4v cubed plus t. And there's our derivative. Wasn't that fun? I absolutely loved it personally. Hope you guys did too. Okay, that's all we have for right now. I'll leave it there.